Hey everybody, in this video we're going to talk about series circuits. It's an extension, of course, of our previous lessons, which were just about resistors in general. I wanted to kind of give some context here of why this is necessary, so I just did a quick Google search of circuit board. This is something that you may have seen if you've ever cracked open an electric device, or if an electric device has something exposed to it. Each of these components in devices such as these have their own purpose, but the circuits themselves get very complicated. So we're seeing hundreds. Here we see, I'd say, about a dozen or so resistors on this circuit board. The little beige things are resistors, and they're connected in different ways, which makes the circuit and the mathematics very complicated. So electrical engineers will help design these resistors, will help design this circuit board so they get the appropriate amount of power going to each component, each microchip, each light, whatever you have on the thing. So I don't know very much about what the circuit boards themselves are for, but I do know that the mathematics gets quite complicated. If this is something that blows your mind, you should check out electrical engineering. If not, well, we just got to learn the math as well as we can in order to pass the tests. So let's get on it. Series circuits. A series circuit is a special type of way that resistors are connected. Series wiring is when the elements of a circuit are connected so that they have the same current. In other words, there is no junction or split between them. I'll read that out again. Series wiring is when the elements of a circuit are connected so that they have the same current, and in parentheses I've written, there is no junction between them. A junction is just a split in the wire. So the way we've been drawing them, we've done a battery like this. Here's a resistor on top. On the same wire, although there's a bend in the wire there is no split between, there's no like branch going off of here. That would be called a junction. If the wire splits into two pieces, that would be called a junction. So they would not be in series. So this is in series. And maybe, I think in the next picture I'll show a combination of two. So in this next picture, this would be an example of not in series. Because of that junction between them, some of the current will go this way, some of the current will go this way. The current might be the same number, but probably not. It's important that they're two separate currents. It's like a stream of water that splits into two pieces. And this third picture, if you've got space, go ahead and draw it. This will be partially series, partially not. I realize I didn't leave much space for myself. This one's a little more complicated because it's partially in series, partially in not. We have three resistors now. This resistor is not in series with anything, but these two resistors are in series. So you could label individually. I'll just write partially series. If you've got some colors, if I were you, I would circle those and write in series. Yeah, I'll do that. I've got space. If you don't have the space, just hold off. So depending on whether or not circuits are in series, we'll use one set of equations or another. There's the whole thing all together. I'm going to see if I can find on my pictures here two resistors that are in series. Probably not, it'll be hard to tell, but we see splits in the wire here. No, I think it'll be too hard to tell. Where is that really good one with the resistors on them? No, it's too hard to tell. We'd have to go to the back side of it. But as you can see, it's just a crazy array of resistors, of circuits, pieces of the circuit. I'd say these two, if these are resistors, they would be in series. Got splits all over. Yeah, probably not very fruitful. All right, let's just get on to the math. So if something is in series, it has a special set of equations. And here they are. First of all, it says that they have the same current, so we'll write that down. The total current is the same as the current in resistor number 1, which is the same as the current in resistor number 2, and so on and so forth. If I have 2 or 3 or 4 resistors in series, they're all going to have the same current. IT equals I1 equals I2 equals ... And the rest of the values are additive. What do I mean by that? Well, the total resistance of the circuit is found by just adding the individual resistances of the resistors. RT equals R1 plus R2 plus ... And finally, voltage, VT equals V1 plus V2 plus ... So in case it's not obvious, the 1s represent the values for resistor number 1, whichever one you name resistor number 1. The 2s represent resistor number 2. And T represents the total current. Also, they sometimes call it the battery current or the equivalent current. So we'll include that here as well. So I'm going to write a brief little sentence here. The T for total is often written as B for battery or EQ for equivalent. The T for total is often written as B for battery or EQ for equivalent. The reason it's sometimes called battery is because the current comes out of the battery, so we can measure that there. The current coming out of the battery will disperse throughout the circuit. So it is your total. And the reason it's sometimes called equivalent is because of usually resistance. If I have a 10 ohm resistor and another 10 ohm resistor, and I put them together, they will have a new resistance, which is the equivalent of just having one 20 ohm resistor. So a 10 ohm and a 10 ohm are equivalent to just a single 20 ohm resistor. Let's see an example of how this plays out. In the circuit below, determine the equivalent resistance and the total current. In the circuit below, determine the equivalent resistance and the total current. Notice the vocab here, we're really just finding two totals. We're finding RT, equivalent resistance, which is the same as total resistance, and total current, which is IT. Here's what the circuit looks like in this case. It'll be I'll draw the battery up top. So it's a 24 volt battery. The resistors are 86 ohms and 47 ohms. My favorite thing about series circuits is that the equivalent resistance is always, well, usually super easy to find. Look at that. Resistance total is just R1 plus R2. So we just got an addition problem here. R total will be 86 plus 47. So our total is 133. Already halfway done with the problem. There's our equivalent resistance, which just means total resistance. So what this means, the reason they call it equivalent is like the amount of resistance on this circuit would be the same if I just had a single 133 ohm resistor. It would act like a single 133 ohm resistor. They would be the same. Total current, we're going to be using Ohm's law to find total current. It would be nice if I had V1 and V2. I could just add those up, but that's not the case. We're going to pull from this guy here. So the thing about circuits is that things like V equals IR, P equals IV, those basic equations are still useful, but we use them directed towards one resistor or a total. So this could be V1 equals I1R1, V2 equals I2R2, or, as we're about to use it, VT equals ITRT. The total voltage in my circuit is equivalent to the total current times the total resistance. So by solving for IT, we'll have our answer. I'm going to just plug in the numbers rather than solve symbolically. It's up to you what you want to do there. So to get our answer, I'll take 24 divided by 133. And the answer will be 0.181. This is a common theme with series circuits and, as we'll see in the next one, parallel circuits. The theme I'm referring to is that there's a lot of short equations that we'll use in succession, one after the other, which we'll see in the next one, which is a little bit longer, a little bit more complex. Okay. Here we won't have a diagram. We'll just use verbiage. A 6 ohm resistor and an 8 ohm resistor are connected in series with a 12-volt battery. Calculate the power delivered to each resistor. A 6 ohm resistor and an 8 ohm resistor are connected in series with a 12-volt battery. Calculate the power delivered to each resistor. In these problems, when you're given so much information, my opinion is that the best step is to write down what is given and what is being asked for. So we'll start with this. Calculate the power delivered to each resistor. That means we have these two individual resistors. We want to find the power of number 1 and the power of number 2. They're not asking for the total. It says the power delivered to each one. So if they said the total power throughout, we would do PT, but this is not what they're asking for. We'll say that this is resistor number 1, this is resistor number 2, so R1 equals 6 ohms, R2 equals 3 ohms. And hey, while we're at it, it says they're in series. So that means our total is just those two added together. Whenever you have both resistors in a series circuit, you may as well add them to get the total. I know I'm jumping around a bit, but let's just get the last one written down. V total, it's the battery. I could also write VB, same thing, is 12 volts. So I jumped the gun a bit with this total, but pretty important. With series circuits, you should just find the total if you've got them, if you've got the individuals. So let's see, we're trying to find the power delivered to each resistor. For reference, here's the equations of power. Here's a few that we've used in the past. Power equals I times V. Power equals V squared over R. Power equals I squared R. The reason that I think this one is the most relevant to us right now is because it's a series circuit, and that means that current is the same in both of these. I know I do have the voltage of the total, but I don't have the voltage of each individual resistor. I have resistance for both of them, and if I find the current, I will then have the current for both of these. So there's many ways to solve these problems. My opinion is that you just go and find whatever you can. Here we see we have V total, we have R total, so may as well just complete that equation. Vt equals ITRT. So I'll plug in the numbers. You could solve symbolically if you wish. I think these are a little quicker to actually just plug and chug. So 12 equals IT times 9. We'll divide both sides by 9 and get 1.3 repeating, or just 1.33. Okay, I have IT, but hey man, look at the equations. From that last page, IT equals I1. Oh, that's written wrong. Let me look at the one I wrote down. IT equals I1 equals I2. That means all the currents are the same. That's the definition. It says they're connected so they have the same current. So now that we have the total current, we also have I1 and I2. So the problem is actually almost done. Looking at the equations, I have R1, I have I1. I can go ahead and find P1 with this equation. P1 equals I1 squared times R1. I'm just throwing ones on those. Same with P2. I have I2, I have R2, so now I can get P2. So P1 equals 1.33 squared times 6. It's about 10.6. 10.6 watts. And for P2, (1.33) times R2, which is 3. So for that, it'll be 5.31 watts. So there you have it. To solve series circuits problems, my advice is to always, if you're not sure what to calculate, just calculate something. It will be useful. It will contribute in some way, and you'll eventually get to your answer. There's only so many things that you can find. If, for example, if I found voltage 2, or, well, there's just always some way to get there. Right? My advice is to find something. So like we had here, there they gave us these two resistances, so I was like, I'll find the total. There it is. There's our total. I ended up using it over here. So just pick something. There's only a few equations that you can pick from. One more thing to add here, a final note. I wanted to talk more about it, but the video is getting a little lengthy. In circuits, power is always additive. Meaning you can add to get a total. So power is just the amount of energy consumed per second. So if you've got, this is the amount of energy consumed per second, so the total energy consumed by the circuit would just be adding those together. If you don't understand that, don't worry about it. All I'm saying is, here's another equation that we might use later. I want you to write it down. And that is useful for any type of connection, whether series or not. All right. Thanks for watching. Keep up the good work, and let me know if you have questions.